Okay, good morning. Here is the notes for section 3.2, where we're going to be talking about logarithmic functions and their graphs. So in the last unit, you learned about the exponential function. And the exponential function is used whenever things grow very, very, very quickly. And the logarithmic function is something that we're going to use whenever things grow very, very, very slowly, like just any item that grows very slowly over time. So we're going to be using the common logarithmic function, which is a log with a base b of x, and then we're going to use the natural logarithmic function, the natural log of x, and that has a base of e. And we're going to see that the logarithmic function with the base a is the inverse function of the exponential function f of x equals a to the x. So the logarithmic function with base a is defined as, I'm going to say log base a of x. For x is greater than 0, a is greater than 0, a does not equal 1, if and only if x equals a to the y. So just as you're going along, if you see the notation written like this, you would say log base a of x. So the equation x equals a to the y in exponential form is equivalent to the equation y equals log base a of x in logarithmic form. So when evaluating logarithms, remember that a logarithm is an exponent. This means that the log base a of x is the power to which a must be raised to obtain x. So I know that a lot of times when students hear all of that, their reaction is, huh? What? So I like to put numbers into things first of all. So if log base 5 of 125, we're looking for the answer to that, right? We want to know what is the answer. So whenever I'm looking for an unknown answer, I would use a variable, and then I remember that my exponential form is where's the exponential form? It's back up here somewhere. I just want to make sure to use, so exponential form x equals a to the y. So sorry, this should be a y over here. So 5, the base a is 5. 5 to what power gives me 125? And if I know my powers of 5, 5 to the 1 is 5, 5 squared is 25, 5 to the third is 125. So I could go ahead and answer and say y equals 3. But the key to that is really understanding that you want your base to your power equals your number. So here in example 2, I want my base to my power to equal the number. So 10 to what power equals 300? Well, there's not an even power here. 10 squared is 100, 10 to the third is 1,000. So 300 is somewhere in the middle there. So that's where your calculator comes in. Whenever you have an x as an exponent, and you have no way to figure out what the value of x is, that's where you're going to be able to use a logarithm, because to pull that exponent out of being an exponent. So you need an inverse function. Right now it's an exponential. you need the inverse. Just like when we have x squared, well, the inverse of x squared is the square root. We need to be able to do the opposite to our function in order to solve it. So the inverse of this exponential is the logarithm. And so in your calculator, the logarithm is already base 10 is the standard in your calculator. So if you do log of 300, it's understood that the base is already 10, and the answer to that, and I have to do mine in reverse order, so I put in 300 and I hit the log button, it's 2.477. And we knew that the power of 10 here, it was going to be somewhere between 2 and 3, right? Because 10 to the second was 100, 10 to the third was 300, so we needed something between 2 and 3. So that logarithm is what's going to enable us to solve those problems. So I want to do some examples for you. We're going to use the properties of logarithms. So the log base a of 1, and basically a to the, so whenever I'm solving logarithm problems, I convert back and forth between logarithmic and exponential forms. So I'm kind of thinking of this in terms of a to the what power is always 1. So that's going to be 0. So here, a to the what power is always a, 1. A to the what power is equal to a to the x power. And then now we have an exponential form, a to the log base a of x. That's just going to equal x. And if I have a log base a of x equals log base a of y, then x equals y. So we'll do some more examples in class so that you guys can get these down. For now, let's keep moving. In example 3, I've got a logarithmic equation and I want to find what x is. So if I'm not able to punch it into my calculator with the log button, which I can't do log of x, I'm going to switch back and forth between logarithmic and exponential form. So I can take my base, which is 7, to my answer, which is 1, equals x. So x equals 7 here. Now, we'll do some more examples of that in class. But the key is to convert, and let me write that down. Convert between exponential and logarithmic form to solve equations. Alright, so the graph of the logarithmic function, and we want to know, is it increasing or decreasing? And that is one that I want to pull up. So let me get the parent function and sketch it over here. So the parent function of the logarithmic equation has an intercept at x equals 1, or at the point 1, 0, and it has the y-axis as an asymptote, and then it increases very slowly. So this is the parent function, f of x equals log base a of x, and it is increasing. And the domain, actually, we don't take logs of negative numbers, so we're going to start our domain at 0, and since it's a asymptote, I want to use a parenthesis there, but I can take the logarithm of very large numbers. The range actually goes from negative infinity to positive infinity, and the intercept is at 1, 0. Also, the graph has the y-axis as a vertical asymptote. It's a reflection of the graph of f of x equals a to the x in the line y equals x. And if you recall our discussion about inverses, all inverses are a reflection over this line. So now I want to take a look at the graph of the function f of x equals log base 3 of x. So we want to be able to plot this, and let me just show you how I'm always converting back and forth between logarithmic form and exponential form. So let me write some exponential equations involving, I'll say equals y instead of f of x. So 3, if y is 0, let's say, and then we go 3 to the 0 equals 1. If y is, I'm trying to pick powers of 3 here, so if y is 1, 3 to the 1 equals 3. If y is 2, 3 to the 2 equals 9. So if y is negative 1, 3 to the negative 1 equals a third. And if y is negative 2, 3 to the negative 2 equals a ninth. So now I've got enough points where I can plot my parent function. So at 1, 0, I've got my intercept, and then 3, 1, and then 9 is way out here, and I'm just going to go up to 2. So you can kind of see the functions increasing very slowly. Then between 0 and Between 0 and 1, our graph just starts to go down. Negative 1, negative 2, and we get closer and closer to the axis. So this graph follows the parent function pretty exactly. So the only thing that changes by changing the base is kind of like this slope, or how quickly the curve approaches the asymptote and how slowly it grows. So next we have the natural logarithmic function, which is the inverse of e. So that's the inverse of our base e. So if I take the natural log of 1, I still get 0. And so that's like you have a little bitty e in here, and e to the 0 power, anything to the 0 power is always 1. So the natural log of e is 1 because e to the 1 is e. The natural log of e to the x is x. E to the natural log of x, well, those are inverses of each other, so they are going to, if we have a natural log and we want to figure out what x is, we can raise it to the e power. So if the natural log of x equals the natural log of y, then x equals y. So for right now, we want to evaluate the natural log of 10, and it's 2.3. So you're just going to practice using your calculator to enter in that natural log function. So the domain of the function, natural log of x plus 3. So let's look at the natural log of x function. The parent function is the same as the log function. So here's f of x equals the log of x. And then if we're going to add 3 inside the parentheses, that is going to be an h value. So we are going to move that. So here's an h value of plus 3. So h is actually negative 3, so we go 3 to the left. So we're going to go 1, 2, 3 for that critical point, and then we're going to have the same graph. So the domain of that function, what we've done is we've just moved our asymptote from 0, from y equals 0, we've moved it over to negative 3, and then we're still going to go up to infinity on that graph. So the domain is going to be whatever our h value is to infinity when we have those transformed functions. So now we want to take a look at a real life situation where logarithms are used and describe a real life situation. So anything where things increase very slowly. So the example I always think of is the Richter scale for earthquakes. They use logarithms for those. But let's take a look at interest. And we're going to have our formula given. And this is actually a formula to tell us how many times the original will our money increase. So we want to look at what all of these variables are. And let me move my camera before I get going too far here. So we've got our principal, we've got our interest rate, we're automatically given that we're compounding continuously, and k is the multiplication factor. So in our question, how long will it take? So we're looking for the number of years. And then, so now when they say double in value, we have to think about, well, how many times the original is that? Well, that's a k value of 2. So if we substitute into our equation the natural log of 2, then that's going to tell us our answer. And it makes sense that we would be using the natural log, because it's the inverse of e, and e is the variable that we use when we compound continuously. So looks like at that interest rate it would take us 11.55 years to double our investment. And then if we want to triple, we just plug in a value of 3. So I'm going to take the natural log of 3 and then divide by 0.06, just because that's what the formula says to do. So it would take 18.3 years to triple our investment. So that's one application of logarithms, and not sure how many word problems are actually going to be assigned, but if you were in an honors class, you would probably have a lot more application problems. The logarithm is so useful in actual solving engineering problems and financial problems and all sorts of things like that. So thanks for watching.